Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods, and in this lesson, I'll introduce yet another time series modeling approach. This time, this model is applied more generally to multivariate time series. The model presented in this lesson is the simplest formulation of the state space model. More complex state space models can be developed in a similar way as presented in this lesson. The idea behind state space models is that the driving forces behind the evolution of variables or time series are, at least partially, not observable or measurable. For example, one's education level can be driven not only by exogenous factors such as access to schools and income level, but also by many hidden factors such as special abilities which cannot be measured directly. Economic theory suggests that macroeconomic variables such as GDP are driven by unobservable factors, for example, technological change. The VAR model introduced in this course only can account for exogenous variables, which are measurable and observable. The state space model is an extension in that it can also account for hidden factors. Formally, a state space model for an observed multivariate time series of dimensionality W, yt in this slide, depends linearly on an unobserved or hidden multivariate time series xt, also called the state process. Yt is thus the linear transformation of xt plus a white noise process. This equation means that the observed time series process yt is dependent on the state process xt. The hidden process xt takes the form of a var of order 1 if the ft does not depend on t, or more generally a so-called Markov model. We'll learn in the next lesson that the ARMA model is a particular case of this model. In the model formulation from the previous slide, the first equation is called the state or transition equation, and the second equation is called the observation or measurement equation. Some important assumptions are as provided on the slide. Most importantly, the error process Vt and Wt have mean zero, but their covariance matrices can depend on t, hence modeling contemporaneous dependencies. For most of the discussion of the state space model in this lecture, we assume that the data are from a Gaussian process. However, it does not have to be, as we will learn about a more generalized form of the model in the last slide of this lesson. Here's a subset of particular cases of state space models. For example, the AR model and the VAR models are easily derived as state space models since the hidden process xt model is defined as an AR-VAR model. In fact, many econometric models, in particular time series models, can be written in state space form. This obvious flexibility of the state space model approach has contributed much to its popularity in recent years. We can define a similar property of stability for a state space model as for the VAR model. If we consider the special case in which the covariance matrices of the error terms Wt and Vt do not depend on time, then we have stability if all eigenvalues of f lie strictly inside the unit circle. This property is very similar to that of stability of a VAR model. We can also guarantee a unique solution to the system of equations under the stability condition. Here we see the direct connection between the state space model and the ARMA model. If yt is a stationary ARMA model, we can write yt as a state space model where yt is a linear transformation of the hidden process xt, and xt is a var of order 1 model with the matrices f and g provided in this slide. The F matrix in the VAR model for xt is merging an identity matrix with the last row, including the AR coefficients. The G matrix is the linear transformation of xt and is simply the vector of the MA coefficients. Last, the error term process includes zeros except for the last term, which is specified by zt plus 1, the error term of the ARMA process at time t plus 1. The state space model introduced in the previous slide is the simplest representation of a state space model. We can generalize this model by modeling the conditional distribution of the observed time series yt given the hidden time series xt with a more general distribution which represents the observation distribution. Similarly, we can describe the one-lag dependence of the hidden process xt or the conditional distribution of xt plus 1 given xt with a more general distribution, which represents the one-step transition density of the Markov process. This model applies to more general distributions, for example, time series of Poisson counts or intermittent spikes. This generalization is in the same realm of generalized modeling when extending the multiple regression model to generalized linear models. The distribution of the data or of the error terms does not need to be normal. It can take other distributions such as the Poisson distribution. In summary, in this lesson, I introduced the model, the state space model, which applies generally to multivariate time series. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Studio School of Industrial System Engineering. This lecture is on other time series methods. On this lesson, I will continue with the introduction of state space models with the focus on estimation and prediction. Let's return to the formulation of a state space model. A state space model for multivariate time series of dimensionality W yt in this slide depends linearly on unobserved multivariate time series xt, also called hidden process, since it is unknown. Yt is thus the linear transformation of xt plus a white noise process. The hidden process xt takes the form of a var of order 1, or more generally a Markov model, assuming the transition probability matrix ft depending on the time. In practice, the linear transformation matrices GT and FT are assumed not to depend on time, although we can generally define a model with these matrices varying in time. Similar to prediction for ARMA or VAR models, we're interested here in finding best linear predictors, but this time not for yt, but for the state variable xt given the past data up to time point s. That is, we're interested to produce estimators for the underlying hidden signal, unobserved signal xt, given the observed time series data yt. This will be denoted by P of index S of xt to be the expectation of xt given a time series y up to time s. Because we're interested in a linear predictor or estimator given the observed time series y rather than the unobserved time series x, we write P of index S of xt as the linear combination of y0, y1, y2 up to ys, where a0, a1 up to as are matrices if the time series y is a multivariate time series. Now, the idea of prediction takes three forms, depending on whether S is smaller or larger than T or equal. The three forms are prediction, filtering, and smoothing. Prediction is finding the one step ahead or multiple steps ahead prediction of xt given a past data up to time t, excluding the time t. In the formulation above, S is strictly smaller than T. This is a common way to define prediction. Filtering is when S equal to T, that is, estimate X at the current time point T. We can view this as an imputation, where estimation of the unobservable hidden process xt given only the current time point data, yt. The last problem is called smoothing, and it is when S is larger than T. Smoothing means that we approximate or impute the unobservable process xt given the observed time series y up to time point s going beyond the current time point t. that is using past and future ops information to estimate xt at time t. Again, this is an estimation, not prediction of xt. Of course, this assumes that the time series y has been observed beyond the time point t. It's important to note here that we're interested not only in the prediction of the process x, but also in the approximation, imputation, estimation of this process, since it is unobserved, and hence we may be interested in its behavior over the period of time we have already observed the time series y. The solution to these problems is accomplished via the Kalman filter and smoother, and is the focus of this lesson. Let's take a closer look at one-step prediction of xt based on the past observed data yt minus 1. Similarly to the linear prediction approach in ARMA and VAR models, we seek to minimize the mean squared error omega t in this slide. We obtain these predictions using a recursive algorithm. We first begin by determining x1 hat, or the prediction of the process x at time t equal to 1, given the initial value of the process y0. Then the recursive formula for yt plus 1 hat, given xt hat and yt, are provided on the slide. Thus, according to this formula, we obtain xt hat from x1 hat, y1, x3 hat from x2 hat and y2, and so on. This is why this is a recursive algorithm. Furthermore, for each step ahead predictions, we can apply again a recursive algorithm in which we begin with one step ahead predictions, then recursively multiply the one step prediction with the matrix of the coefficients, or the transition matrix ft of the Markov model for xt. Note that if ft depends on time, we will need to project ft for future time points t in order to obtain this prediction. The linear transformation matrix F and the transition matrix G are both unknown, and they need to be estimated. Other parameters in the state space model are the covariance matrices of the error processes Wt and Vt. The parameters in the state space model are estimated using the maximum likelihood estimation under assumption of normality. That is, the error processes Wt and Vt are assumed to be Gaussian processes. Under this assumption, the likelihood of the state space model can be expressed in terms of the one-step prediction errors provided in the previous slide. Note that the one-step prediction of xt gives us the one-step prediction of the time series yt, denoted here yt hat. When estimating the model parameters, the likelihood is a function of the parameters given the observed data, the time series y in this model. Maximizing this likelihood is, however, quite challenging due to the presence of the hidden process xt. Advanced statistical modeling is thus needed to estimate a state space model. In summary, in this lesson, I provided a higher level understanding of the prediction and estimation of a state space model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on other time series methods. In this lesson, I will illustrate the state space modeling approach with the simplest model. One of the simplest state space models is a random walk with error measurements. In principle, such model can be extended to any ARMA or VAR model with measurement errors. To be more specific, the state equation is that of an AR of order 1 and coefficient equal to 1 corresponding to a random walk. But we do not observe xt. We observe instead yt, which is xt plus an error measurement vt. This is how we can simulate such a process in R. We simulate two vectors of uncorrelated normal distributed realizations or observations, denoted here with W and V. To obtain the random walk at time t, we sum up all the values in W up to time t, denoted here with x. Then the process y is simulated by adding x and the error term v. Next, I plotted both the observed process and the hidden process X. The plots are here. The hidden process is a random walk, and hence it is non-stationary, as we can see from the plot of this time series on the right. The process Y captures some of the pattern in X, for example, an increasing trend over time, but with much more variations. Can we recover X from Y by fitting a state space model? The simplest R function in R that we can use to fit a Kalman recursion for a state space model is the function k smooth 0, which returns the filters and predictions as well as the smoothers using the Kalman recursive formula. This function assumes that the model matrices, including the linear transformations of Y and X, but also the covariances of the error terms, are all time invariant. If it is the simplest implementation of a state space model. The function k smooth 1 is a more general implementation, for example, of a state space model. Note that the objective in state space model is not that of predicting Y, but that of predicting filtering and smoothing X as provided by such functions which perform the Kalman recursion. Here I'm providing the R code for plotting the one-step ahead predictions for xt obtained from the object k as fitted in the previous slide, and specifying $xp, which stands for prediction. We can also obtain the filtering and smoothing versions of by specifying $xf and $xs. In each of the three plots, I'm overlaying the simulated X process along with the prediction, filtering and smoothing of X, and the 95% confidence intervals. These are the plots of the prediction, filtering, and smoothing for xt in this order. The lines are the prediction and the points are the observations of the process X. As expected, the prediction has much higher uncertainty, in other words, wider confidence bands than filtering or smoothing. The smoothing also has tighter confidence bands, since the imputation of xt is done using more data than for filtering. In all three settings, we accurately impute the hidden process xt. The confidence bands include most of the simulated xt values for all three settings, and the observations are close to imputed values of the process xt. Thus, even though we did not directly observe xt, we can still uncover it from the observed process Y with high accuracy. In this lesson, I briefly illustrated the implementation of a very, very simple state space model using the R statistical software. Thank you.